Hello everyone, welcome to my group theory lecture. In this lecture, we continue to study Lagrange's theorem. Okay, so uh, here's more about the equivalence relations. Right, so here's an important theorem. Let R be an equivalence relation on a set S, then uh, I don't know if actually this is correct one. Yeah, I'm supposed to talk about. Okay, sorry about that. So I just wanted to make sure that I didn't miss anything. Okay, so we begin with the following theorem about equivalence relations. A very important theorem. Let R be an equivalence relation on a set S, then S as a union of or the yes. I think I was. Yeah, I was missing something because that this you don't know what this is, right? Okay, you don't know what this is. I think yeah, I'm sorry about that. The Let me go back. Okay, when I was writing this definition about the an equivalence relation, I forgot to mention one thing very important. So I'm gonna do that. I think I need to fix my also the uh, slides later on, but I'll explain here. Okay, so let R be an equivalence relation. Okay, equivalence relation on uh, a set S. Of course, here every time I just say a set, what I mean is uh, non-empty set. Okay, there's not much you do with the an empty set. So it is a non-empty set S. Well, in this case, right? So uh, and also let so A B in S. Okay. So we define the following notation: bracket of A. So what is this? Bracket of A is defined to be, okay, all right, then this is definition, colon equal sign is the define, okay, this is define. Okay, this is a set of all elements in G such that B is related to A. So the collection of all elements in G that are related to A, that is called, that is denoted by this notation. And we call it the equivalence, okay? Equivalence class, equivalence class, equivalence class of A. Okay, so that's the equivalence class. Now I think we can get back to the theorem. Okay. Right. So coming back to theorem. Now third time is charm. So hopefully everything goes well. Without actually missing anything. So let R be an equivalence relation on a set S, then S is the union, okay, the union of all equivalence classes. Now I can use them, okay? So because you know what an equivalence class is, right? And second condition, and second property is that for any A, B in S, either two equivalence, the classes, right, A and B are the same, or they are. Oh, here's another mistake. I'm sorry. It's supposed to be. It's not equal. It's supposed to be intersection. So A intersection B. Sorry about that. I'm gonna fix that later. A intersection B again is empty. So the class of A and class of B are disjoint. Okay, the intersection of the class of A and equivalence class of B is empty. So this means that an equivalence relation R on a set S partitions S into equivalence classes. Okay, the set of all equivalence classes in this case, right? This is the one, is denoted by S mod R, and is called the quotient set of S modulo R. Okay. Well, this itself is very important. Okay, but also for us later on, this from here, right? We can come up with a new group structure. Excuse me, which is called, the a quotient group. Not every equivalence relation leads to a quotient group, but a particular type of equivalence relation does. You might have guessed already, a congruence relation, okay? A congruence relation. So if an equivalence relation preserves the group operations, then that leads us to a quotient group. So earlier that equivalence relation, right? Congruent, modulo, and as one of those the congruence relations, and that's gonna lead us to construct a quotient group out of the set of all integers. Or actually, they're not just set of integers, but the integer group Z with addition. So we are gonna talk more about those things later on. Okay, so let's move on. Let's prove this theorem. Okay, so let me get to my notepad. So theorem R is an equivalence relation on a set S, then S is the union of all equivalence classes A in G, and 2 for any 2 elements A, B in S, either A, the class of A equals class of B, okay? Or class of A intersection class of B is empty. So they are disjoint, right? They are disjoint. Okay, so we're gonna prove this. I need to move to next page. By the way, before actually I prove it, I'm gonna. So the earlier I mentioned the following thing. You might not get this clearly. I said, okay. So an equivalence relation on a set S partitions S into equivalence classes. Okay, partitions into equivalence classes. What does that mean? Actually, this is what it means. Partitions. But I'm going to actually visualize it so that actually you can understand it better. All right. So I'm going to actually draw this. So that depicts the set S, okay? And we have S with the equivalence relation R, okay? So in that case, we can, right, if R is an equivalence relation, then we can partition, okay? We can partition this set into equivalence, the equivalence classes. Okay, so that's class of A. This is going to be class of B, class of C, class of D, class of E, class of F. Okay. S might have more elements, many more elements, or possibly like infinitely many elements, right? But they all belong to these equivalence classes. Okay, so again, some of them could belong to the same, like equivalence class here. Some of them belong here. Some of them belong here, and the what is that? Any two equivalence classes, right? If they are not the same, they have to be disjoint. They have to be disjoint. No intersection, okay? So that's why like we have this picture, right? So we can partition just like this. We can divide, partition S into, right? These pieces, like here pieces are, the equivalence classes. Okay, so now we are ready to prove it. Proof. So first one, okay, let's show the first one. Clearly, the union of all equivalence classes, right, as a subset of S, obviously, right? If you know, well, I'm sure you do, the basic properties of the set, subset, and so on and so forth, right? Each equivalence class is a subset of S, so their union is also, subset of S. So that's it. So we're gonna show the other way around. Okay, so S is a subset of the union of the all equivalence relations, so that they are the same thing. So let A be in S. So we randomly pick arbitrary element A, then by reflexivity, A is related to A, right? A is related to A. That means A belongs to, right? A belongs to its own what is that? Equivalence class, right? A belongs to its own equivalence class. Okay, so that means right? Also, at least it's got A itself. Okay, so that's not empty set. And this is a subset of, right? So equivalence, the class of A, right, is a subset of or union of this is sort of like a bad notation, so just bear with me. So here A is a particular, the element that I have chosen A. This is just the generic one, okay, generic A. So these are not actually the same A. These are not the same A. So I hope I'm not confusing you. if you wish, actually, maybe, I could have done a better job by picking actually different letter. So, B or C, that's okay, right? But as long as, you can distinguish, okay? So this is a particular A I chose now, but this is generic A, okay? I'm keeping this because that's the one, I used in the, right, what is it, in the theorem, okay? So as long as you have that in mind, that's okay, but to avoid the confusion, you could use like different letter, okay, B or C or whatever. Anyway, so this is a subset of S. No, 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 it's not. It is, I know, but that's not what it is, right? So what that means is, of course, here, yeah, you know what? Actually, I'm gonna just change that. Yeah, so I just got the, heart of it, change of heart. So yeah, actually that's better. So let's just choose B, right? Then B is related to B. So B belongs to the class of B, which is not empty. So what this means is B is an element of this whole union, right? So union of the class of A, yeah, that's better. That's much better. Okay, right. So what does that mean? That means, right? Thus, S is also a subset of this all union. Oh, no, not G, S. Or equivalence classes of A. Okay? Looking good. And therefore, hence, we're done. These two are the same. Where hence, S equals union of or equivalence classes, done. Next property, we want to show, right, for any two elements A, B in S, either the equivalence classes of A and B are the same, or, they are disjoint. Okay, so how do we prove something like this? Okay, where if the equivalence classes of A and B are disjoint, empty, set, we are done, right? If not, we will have to show that they are the same thing. So that's the strategy we're going to use to prove this, okay? So here let A and B, so two elements A and B belong to S, but we say these are two distinct elements. If these are can be the same, then they are the same. Then obviously, the their equivalence classes, are going to be the same. So, we can just exclude those, right? I mean, that case, right? So A and B are distinct two elements of S, right? Like I just said, if A equivalence class of A and intersection equivalence class of B is empty. So if these two are disjoint from each other, then we are done. So we now suppose otherwise. Okay? So what that means is we assume that this is not empty. Since this is not empty, then there exists, remember this notation, right? This means there exists an element C in the intersection. Okay, there is at least one element in the intersection, okay, because it's not empty. That's our assumption now. So this implies that, okay, implies that C is in the class of A, and C is also in the class of B by definition. And that implies C is related to A, and C is also related to B. Okay, and this implies, R is symmetry. So C is related to A means A is related to C, and C is related to B. Okay, because R is symmetry. Okay, and that implies A is related to C and C is related to B. So A is related to B. What property did I use? R is transitive. Okay. So we got to that. What does this mean? A is related to B. A is related to B means that, okay, in fact, the class of A and class of B are the same. They have to be the same. It seems pretty obvious, right? But if you want to convince yourself that that is the case, we can actually prove it, okay? So it won't hurt. But let me write that down first. So actually that implies the class of A equals class of B. All right, so we are done, but if you want to convince yourself that that is the case, we can actually show. So, here, maybe I use different color and, right, so inside a parenthesis, right? So to show that, why don't I actually use maybe D, right? So if D belongs to class of A, okay, class of A. So here, I'm under this assumption, right? For me, now it is assumption, but we know it is, right? So R is related to B, then we want to show that these are actually the same, from the concept of equivalence classes, that's pretty obvious, okay? But again, we want to convince even more, ourselves that that is the case, then, we do this. All right, so this implies that D is related to A, right? D is related to A. And also, we have this assumption, so A is related to B. So using transitivity, right? Transitivity, D is related to B. So this means that D belongs to the class of A. So what we have just shown is, class of B. So what we have just shown here is that maybe I'll use different color. Okay. So class of A, I just showed that class of A is a subset of a class of B. Okay, that's what I just showed. And conversely, this time, let's say D belongs to class of B. So that implies that D is related to B, but then also we have this condition, right? So A is related to B, and that implies D is related to B, and since R is a symmetric, so that also means B is related to A. Okay, and that implies by transitivity, D is related to B and B is related to A. So using transitivity, D, we know that D is related to A. That means D belongs to the class of A. Okay, so what did he have just shown now? What that means is class of B is a subset of class of A. Therefore, right, so A is a class, the class of A is a subset of class of B, and the class of B is a subset of class of A. That means what? The two sets are the same, so we are done. Okay, so now finally, maybe not that the less convincing heart, right, now turned into very convincing heart. So you know, it's all good now. Okay, I think this is it, you know, the good point for me to stop. Okay, we still have a lot more to talk about. We haven't even got to the actual topic, our topic, Lagrange's theorem yet. Okay, so we have a lot more to talk about, but I will continue, you know, we will continue our discussion in my next lecture. Thank you.